study out of MIT recently looked at 300 real enterprise AI projects and found that 95% of them failed to produce a measurable impact. These projects didn't fail because the AI was broken. They failed because the companies couldn't prove the models were actually solving business problems. This is why evals, or systematic quality checks, are becoming a central part of technical interviews at companies like OpenAI and Anthropic. They need engineers who can move past checking a single prompt and instead build a mathematical proof that a system works at scale. To see how this works, consider a hospital deploying an AI to summarize emergency room wait times. The hospital needs to know if the summaries are accurate before they let doctors or patients rely on them. Looking at a single AI response is easy. You read it, it looks fine, and move on. But you cannot manually verify 10,000 patient records. When moving from a demo to a production system, the sheer volume of data makes manual checking impossible. Since humans cannot scale to match the model's output, automated mathematical proof is the only way to verify that an enterprise AI system is actually doing its job. Most clients will give you a vague goal, like make the summary accurate. To build a system that can be tested, you have to translate that subjective request into strict binary logic. We do this by creating a rubric. For our hospital AI, we set 2 binary rules. It must contain a wait time and be under 50 words. Hitting both gets a 1. Failing either gets a 0. By applying these rules to every response, we can mathematically aggregate the results. Instead of a feeling that the AI is good, we now have a percentage that represents the system's overall success across hundreds of examples. To make this percentage meaningful, however, we need a ground truth reference point, what we call a golden dataset. This is a collection of prompts where the correct answer has been pre-verified by a human expert. By checking the AI's output against this verified answer key using a rigid rubric, we transform a subjective opinion into objective, defendable data. To automate this process, we build an eval harness. This is a distinct programmatic wrapper, a piece of code built strictly to test the AI, separated entirely from the model itself. The harness manages the entire data pipeline. It pulls a prompt from the golden dataset, feeds it to the model, and then routes the resulting output into the rubric function to generate a score. Because this is handled programmatically, we can wrap the entire process in a loop, allowing the script to automatically score thousands of interactions in seconds. Imagine a factory client needs an AI to extract a safety violation code from incident reports. The code must be exactly 4 digits, no more, no less. Think about the specific logic you would need to write in your harness to score this as a pass or a fail. The solution is a simple check. If the output length is 4 and the characters are all digits, the score is 1. If not, it's 0. The eval harness acts as the automation engine for this logic, allowing engineers to demonstrate accuracy at the scale of a large corporation. Once the harness is integrated into a production environment, like a Docker container on AWS, it provides a continuous stream of data about the model's performance on real-world tasks. This chart shows the final result of that process. By providing 92% formatting accuracy and 99% factual accuracy, you are giving the client the mathematical proof they need to trust the system. Building this evaluation framework requires scoping the specific metric, curating the reference data, and wrapping it all in an automated harness. This creates a repeatable process that allows you to prove your results with numbers. Shifting the focus from reading individual responses to auditing mathematical performance is how an engineer demonstrates that an AI system is ready for the real world.